Hi everyone. We're going to be looking at three different types of variation and relationships between variables that fall under these different categories. The first of which we're going to talk about is direct variation. So I want to look at just a very contextual sort of example that is exemplary of direct variation, first of all, right here. And that would be represented in this graph that you see right here between the time and height of a tree over a course of a number of years, of course. Ultimately, what makes this fall under the category of direct variation is, first of all, the fact that it starts from nothing. So at time zero, there is no height. That's an important characteristic of any relationship that's going to be involving direct variation. And then the other thing that is happening here is that there is this constant rate of change that over time it's growing at the same rate, which ultimately results in it being a linear relationship. And so those two characteristics really define exactly what we see in direct variation, that it starts from zero and then also is a linear relationship. So ultimately, when we have an equation of direct variation between two different variables, so between, let's say, the variable y and the variable x, let's say, it is always a relationship where when you multiply that x variable by some number k and it equals y, that is direct variation. So we denote that particular number k right there to be either known as the constant of variation, or instead of variation, we might also call it the proportionality constant. Because ultimately, in direct variation, you actually have relationships where you can actually use proportions, and that's because the graphs are always going to go through the origin, right? So you can see in the graph right there that there are different lines that are all passing through the origin right here. Every equation in direct variation does. And if you think about why that is, right? If every direct variation equation has to be written over the form y equals kx, well, that's kind of like y equals mx plus b, but the b value is going to be a 0. So, of course, then it has to pass through the origin, right? So let's take a look at some examples here. First of all, where we're asked to determine whether y varies directly with x, right? So if y varies directly with x, ultimately that is equivalent to saying that y is going to be equal to some number k, that's the constant of proportionality, times x, right? And so you see four different equations right here. So if there's a way for you to get the dependent variable y alone equals just the number times x, then it's going to be direct variation, right? So if you take this first equation right here and you isolate the y, you can subtract 2 from both sides and then yield the equation y equals 3x minus 2. Okay, this is an example of something that is not a direct variation equation because of the fact that you've got this minus 2 right here, which would lead to the fact that this line doesn't pass through the origin, right? So if we only had y equals 3x, then it could be direct variation, but it's got that extra plus or minus number. So not direct variation there, right? The next equation over here is 4 times y equals x. If you isolate the y by dividing by 4 on both sides, you get y is equal to 1/4 of x, and therefore you can see that, oh yeah, that's y equals just a number times x. So that is going to be exemplary of something that is indeed exemplary of direct variation, right? The next equation, you'd have to like divide by x, I guess, to be able to get the y variable alone. And so y would equal 8 times 1 over x. Okay, this is something that is not going to be direct variation because you can't write it of the form y equals a number times x. This is actually a different type of variation that we're going to talk about in just a little bit, but yeah, it's not direct variation. And then on the last equation right there, you've got that x divided by y is equal to negative 0.6. So one thing we could do to start solving this to get y alone is multiply by y to undo the divided by y right there. And we get x alone is equal to negative 0.6 y. And then if we multiply by the reciprocal here, so since negative 0.6 is negative 3/5, we could multiply by negative 5/3 to be able to get just 1y right here. And then, of course, multiply the other side by negative 5/3, and then you get negative 5/3 times x equals y. And lo and behold, of course, right, that's an example of direct variation right there. All right, so we want to be able to recognize it in that context, in an equation context. So in other different representations, we're asked the same question right here to be able to determine whether y varies directly with x. So now we want to understand this in graphical context with the first couple examples here, and then also in tabular context with a couple examples at the bottom. So in this first equation, that's graphed right here. You can see that it is a line, and every direct variation equation does need to be a line. But what we need to have happen is it needs to be able to pass through the origin, right? And this one is not. So this right here is not going to be an example of direct variation for us then. In the second graph, you can see it is passing through the origin and as a line, so this is definitely going to be an equation of direct variation. For both these examples, you could really evidence for that by looking at the equations for them, because in the one that we just found right here, the slope is up 1 over 1, so the slope is 1, so the equation is actually y equals x, right? Which would be direct variation, because your constant proportionality would just be a 1, right? But the previous graph that we looked at had like a slope of 2, and then it would actually have a y-intercept at -4, right? And y equals 2x minus 4 would not be direct variation because it's got that extra subtracting of 4, right? Cool. All right, and then at the very bottom there, you've got a couple of tables. So you'd want to be able to determine whether you have a line, right? And then it also goes through 0, 0. So when you look at this first table right here, you can see that the rate of change in the x coordinates is +3, and then the rate of change in the y coordinates is +2 each time. So that means that the slope each time would be 2/3. Okay, so you do have a linear relationship. Has to be 2/3 because it's the change in y over the change in x, right? And then we'd have to also make sure that it passes to the origin. So if you did go like backwards by 3, you'd land at 0, and you go backwards by 2 right there, you'd land at 0. So just go through 0, 0 as well. So this table right here is definitely going to be direct variation, right? And if you look at the last table, you can see, oh, great, it goes through 0, 0, right? So then we just got to check to make sure that it's going to be a linear relationship, and you can see that you're going +1, +1, +1 in all the x coordinates, right? And then here you go -1, +1, +1. So you'd have a slope of -1, but then a slope of 1 and a slope of 1, and those slopes are not all the same, right? So this is not going to be direct variation because it's not perfectly linear. What I would probably predict is happening right here is probably going to get like a V-shaped graph because each of the x values seem to be turning positive or staying positive, right? So yeah, this is definitely not going to be a direct variation relationship happening in that particular table. Okay, so digging a little bit more now into actually like writing equations and things with direct variation. Here we're asked to find the variation constant and then also find the variation equation in which y varies directly with x and y is equal to 96 and x is equal to -6, right? So when we're looking for the variation constant, we're really looking for that number k that I indicated earlier. And then the variation equation, now the variation equation is going to be of different forms depending on the type of variation we're talking about. So far we've only talked about direct variation, right? And so when y varies directly with x, we know that the variation equation has to be y equals k times x, okay? So what we do know is that y is equal to 96 when x is equal to -6. So really, that means that this point, this ordered pair, is going to be an ordered pair on the graph of this equation, right? So ultimately, then, it should be able to satisfy the equation that when -6 goes in for the x coordinate and 96 goes in for the y coordinate, it's going to make that equation true, right? So 96 has to be equal to whatever the constant of proportionality is multiplied by -6. Well, hey, we can actually solve that to figure out what the actual k value is, right? So we could just divide by -6 on both sides then. That's going to be able to go in -16 times to equal k. So voila, we've answered the question of what the variation constant is. So the variation constant has to be equal to -16 as an answer there. And then we can also give the variation equation where it's just going to be y is equal to -16 times the variable x for the variation equation. So we answered both of those things. Perfect. All right, so here we see that the height of a television screen, represented by the variable h, varies directly with its width. So varies directly means that h and w have a direct variation relationship with them. So the one variable h can be equal to some constant of proportionality k times the variable w, right? So one particular TV model has a height of 27 inches and a width of 48 inches. So we want to know what is the height of this TV model that would have a width of 70 inches, right? Okay, so we know that for this particular TV model, it has h equal 27 at the time that it has w equal 48, right? So we could be able to find what this constant of proportionality is between the height and width because they vary directly with one another. So if we substitute in 27 for h, and then have k times the width, 48. Then we can solve to figure out what k is going to be. We'll divide by 48 to get k alone. And we get 27 over 48. Both 27 and 48 are divisible by 3. So if we divide by 3, we get 9 over 16 is equal to k then. So that's an important thing, right? So then we know what that constant of proportionality is between the height and the width. So height is going to be equal to 9/16 times the width in general, right? So for a particular TV model that's going to have a width of 70, well, then we can find the height of that if we just substitute in 70 for the corresponding variable of W, right? So 9/16 times 70 should be able to equal the height, right? 9 times 70 is going to be 630 divided by 16, and then you can reduce that because both are going to divide by 2, so you get 315 over 8, and then you're done reducing at that point in time. As a decimal, it's actually 39.375. Everything was in inches, so there you would have it, right? That would be the height of the TV, given that its width was 70 inches, if it's following this direct variation relationship with that 9/16 ratio between the height and width, right? Cool, cool, cool. All right, so now we want to move to the second type of variation that we're going to talk about here today, which is inverse variation. So to exemplify what inverse variation is really going to look like in a actual contextual example, we can look at that in terms of the area of a rectangle, and specifically the relationship between the height of the rectangle and the length of the rectangle. So here we have that a rectangle has a fixed area of 64 inches squared, right? And to be able to get area for a rectangle, we know that area is always equal to length times width, right? Now we're representing, in this case, length with x and width with y in this case, right? So I can actually put in this fixed area of 64 right here, and then if I just take that equation and I divide both sides by the independent variable x, we would get this equation where y is going to be equal to 64 divided by x, right? That is exemplary of an inverse relationship between x and y. And what you see happen in inverse relationship like that is, for example, if we knew that x was like maybe like 4, okay, then 64 divided by 4 would be that y is equal to 16, right? So a little bigger value in y. But then if we like increase the value of x, and let's say that we increase x to be like 32 now, right? Then we're going to see that y is going to drop down accordingly, right? Because they need to multiply to equal the same number. So we get this inverse relationship between them, right? When one variable value goes up, the other one's going to kind of have to come down a little bit, right? So it's this form that I wrote the equation in that really is the form that will recognize inverse variation in. So whenever you have any equation that is an inverse variation, then it's going to be of this form, that the y variable and x variable are related, that the y can equal some number k, some fixed number k always, divided by the independent variable x. So you'll see in the graph right there that inverse variation relationships are always going to look like that graphically, where you kind of have those two separate pieces, really making a shape that we call a hyperbola. So we want to be able to recognize, of course, the forms that inverse variation can come in, and we'll throw in some of the direct variation stuff here so we can kind of see the similarities and differences between them, okay? So ultimately, just keep in mind that whenever you're dealing with direct variation between the variables x and y, that you should be able to have y is equal to kx, and then whenever you have inverse variation, you should have y is equal to k divided by x, right? So those are the only two types that we've talked about so far, right? So in this first example right here, we have that x times y is equal to -3. If you solve to get the y variable alone, you would have that y equals -3 over x, because you have to divide by x to get the y alone, right? And that would, of course, be inverse variation happening right there, because of it follows that format, right? And this also comes back to like when you think about the original form it was given in, right? The two variables multiply to equal a constant number, similar to like in the area of the rectangle right here, right? That the x times y always equal that constant number of 64. So same sort of thing happening right there, just -3. In the next example right here, we have that y minus x is equal to 1. If you get the y alone, you would have that y is equal to positive x plus 1. Okay, that's not going to be inverse variation, right? Because it's not a number divided by x. And then neither is it direct variation because it's got that plus 1. So this is going to be neither of those two particular categories. And then in the third equation, you have that y is equal to x over 2. So if you rewrite that just a little bit, it's equivalent to y is just equal to 1/2 times x. So that would be like a number multiplied with x, right? X is not on the bottom of the fraction. So this is an example of direct variation, because it is y is equal to k times x, of course. Okay. All right, when you look at the tables now, and you look at this table here, first of all, you'll notice that, okay, so maybe there's a pattern linearly, right? So maybe this is direct variation because you got +2, +2, +2, and then it goes +6, +2, +1. Okay, so the slopes are changing because it goes from 6 over 2 to 2 over 2 to 1 over 2 or 3 to 1 to 1/2. And yeah, so that's not working, right? It's not direct variation. One thing that you'll definitely notice is if you look at these couple of numbers right here, the x and the y, if it was inverse variation, the x and the y would always have to equal the same number all the way throughout. And if you multiply those two numbers with each other, you get -24. And then if you multiply actually all of the xy pairs together with one another, it always equals -24, right? So that actually is indicative of the fact that this is inverse variation, right? So it does follow that relationship, y would equal number divided by x. Okay, and then in the last example here, it looks like you're going +1, +1, +1, then it goes +2, +4, +8. Really, actually, it's just kind of like powers of 2, right? So this would not be direct variation. And then also, if you were to like multiply x's and y's with each other, the product there is 2, but the product there is 8. So it can't be inverse either. Ultimately, this is an example of something that is really an exponential equation because it's just y is equal to 2 to the power of x. Neither inverse nor direct variation. So we can just say this is neither of the two since we were only asked to decide between direct variation and inverse variation for now. Okay. All right, let's start using inverse variation a little bit right here. So we see that x and y vary inversely with one another. So the meaning of that is just that y is going to be equal to the number k divided by x. What we want to do is we want to find the constant of variation, and then also the variation model when x equals -1/8 and y is equal to -1/10, right? So constant of variation just means to find that k number that fits the model, and then our variation model, of course, has to be that y equals k over x, because it's inverse variation. So since we have these given x and y values, we can substitute them into the model y equals k over x, and then get -9/10 for y is equal to k, the constant variation, divided by -1/8. Okay, and then we should be able to solve to find that particular k value in this relationship. So since right there we're dividing by -1/8, that is the same thing as -8 times k, right? And so then we have this, and then we'll want to solve for k, which means then we'll want to divide by -8 to cancel it out. And then here we could just write it as multiplied by -1/8 instead of writing it as divided by -1/8 because it's a little easier to compute mentally then. So you'll just multiply across then. So multiplying negative times a negative is going to be +9, and 8 times 10 is 80. 9 and 80 don't have any other common factors besides 1, so it's as reduced as we can make it. So k is going to be equal to 9/80ths. So then our constant of variation, we just figured that out, is going to be 9/80ths then. And then we should be able to write the variation model. So y is supposed to equal 9/80ths over x then for the variation model. But then, like, you have a fraction within a fraction, and that's not considered simplest in math, so we want to write this in a little better form. So y is going to be equal to just 9/80 and x both at the bottom right there would be a more proper way to write that for what this inverse variation equation is going to be. There, now you can see it. Beautiful. Okay, so another great example right here. So the amount of time t it takes, and then the number of volunteers, represented by n, for setting up chairs at an outdoor graduation event, they vary inversely with one another, right? So t and n do. So that tells us then that t is going to be equal to some constant of variation divided by n because they vary inversely with one another, right? It tells us that it takes a group of 8 volunteers 2 hours to complete the setup. Find the number of minutes it would take 12 volunteers to set up. Okay, so it takes a group of 8 volunteers 2 hours to complete the setup. So 8 volunteers is really going to be equal to n, I guess. So I'll just say 8 is equal to n, because that's the volunteers, n. And then it takes 2 hours, that's the amount of time, so t is equal to 2, right? So we can say that 2 should be equal to the constant of variation divided by 8. And then if we solve to get the k alone, we can multiply by 8, cancel that, and multiply by 8 here. And then we get that 16 is going to be equal to the constant of proportionality, right? So then with that, we should be able to find the number of minutes it would take 12 volunteers, right? So we know that y is equal to 16 over x. Actually, it's t equals 16 over n using the variables we have, right? And then with 12 volunteers, we can substitute in 12 for the number of volunteers, and 16 over 12 should be the time that it takes. 16 over 12 is going to be 4/3. So since everything that we did over here was in hours, this would be 4/3 hours. And then we're asked for the number of minutes. So you could just multiply that by 60. That's going to come up to be 1 1/3 hours. So 1 hour and 20 minutes. So it's going to be 80 minutes of time then for the 12 volunteers to get that all set up. All right, and then the very last type of variation that we'll look at here is joint variation. So ultimately, joint variation is going to have a relationship where you have a y variable, some sort of dependent variable that is alone, that you can write as your constant of variation, k, but then multiplied by lots of other different variables. So like X and Z and W and H and J and however many variables you want. So there just needs to at least be like 2 or more variables for it to be joint. Because only if it was only just X, right, they'd be direct variation. So you got to have like at least 2 variables or more, and you can have as many variables as you want. And that's what we call joint variation. All right. So we're going to look at just a couple examples here. So this first example is the volume of a cylinder, V, does vary jointly with the square of its radius, R, and its height. The volume of a cylinder with radius 6 centimeters and height 30 centimeters is approximately 3,393 centimeters cubed. What is the volume of a cylinder with radius 4 centimeters and height 15 centimeters? Okay, so we know that the volume varies jointly, so we've got to have lots of different variables, and it varies jointly with the square of its radius r and its height h. Okay, so our volume is going to be equal to some constant of proportionality k, and it needs to vary with not only the radius, but it says the square of its radius, which means r times r, or r squared, okay, and then also the height of the cylinder. So the volume of a cylinder with radius 6 and height 30 centimeters is approximately 3,393 centimeters cubed for the volume. So we should be able to plug all those things in. We can plug this in for the volume. It's going to equal whatever the constant of proportionality is multiplied by r squared. So the radius is 6, so we want 6 squared, and then the height is 30. So yeah, you have 36 times 30, which is going to come out to be 1,080, and then times your constant of proportionality should be equal to 3,393. Then if you divide by 1,080, you can figure out what that constant of proportionality is going to be. And then we get that k is going to be about 3.1416. Ultimately, what it really is supposed to be is it's supposed to be pi. And so I'm just going to change that to pi, and then we know that the variation equation that we actually have is that the volume is equal to pi times r squared times h, where pi is the constant of variation. That's the true volume for a cylinder, right? So then using that, we can figure out what the volume of a cylinder with radius 4 centimeters and height 15 centimeters is, right? So volume should be equal to pi times 4 and then squared and then times 15. So that's 16 times 15, which is going to be 240. So 240 times pi centimeters cubed would be that volume of that cylinder there. And then finally here we have that we want to find an equation of variation in which f varies jointly as g and h, and then inversely as the cube of j. So let me pause right there and let's process what that really means. So it says that f varies jointly. So jointly means that you should have multiple variables multiplied with a constant of variation, right? So f should be equal to then your constant of proportionality k, and then it varies jointly with G and H, so then times G and H. And then we have another type of variation in here that says inversely. So that means that we would have to divide by whatever variable or variables that would be. And it says with the cube of J, which would mean J to the third power, right? So then we divided by J to the third. So this right here is going to be the equation of variation generally. But then there's that k that's always a fixed number that we should be able to find because we are given the different values of the variables that hold at a specific point in time. So if we substitute in all of those values, we can put in 8 for f, and we have k, and then g is 16, h is 3, and j is -1 that we want cubed. All right, so we'll get 16 times 3 is going to be 48 times k. And then when we cube -1, -1 times -1 times -1 is -1. And then 48 divided by -1 is just -48. So -48 times k is going to be equal to 8. And then if we divide by -48 to isolate the k, divide that by -48, you can reduce that fraction of 8 over -48 because both are divisible by 8 actually, giving you a 1, and then 6, -1/6 is equal to k. So then, yeah, for the equation of variation, then it's just going to be that y is going to be equal to -1/6, so really just negative gh over 6j cubed, and then that shouldn't be a y, I guess, because it said that f varied with everything. So that should be it.